Hello, everyone. Thanks for joining the presentation. My name is Peter Scarfe, and I am the creator of Workers for LabVIEW. And this presentation is going to be about what's new in Workers 5, which is the latest version of the framework that was only released a few weeks ago. This presentation should take about 45 minutes, and I'll do my best to answer any questions afterwards. So let's get straight into it. The breakdown of the presentation looks like this. First, I'll introduce what Workers for LabVIEW is, for those of you who are new to the framework. And then I'll walk through the Workers development tools, giving focus to the new tools in Workers 5. Then I'll present the new messaging APIs that you can now create for your workers. And finally, I'll demonstrate how you can create API abstractions using the new Public API Builder tool in Workers 5. Okay, so what is Workers for LabVIEW? Workers is a framework that helps you to create asynchronous applications in LabVIEW using simple LVOOP, which is object-oriented LabVIEW, queued message handlers in the style of the LabVIEW queued message handler template. So to compare it to other frameworks or design patterns that you are probably familiar with, I'd say it's a cross between the LabVIEW queued message handler template and the Actor framework, because it combines the simple and well-known development style of the LabVIEW queued message handler template with many of the object-oriented features of the Actor framework. Workers provides a range of development tools to help you efficiently develop, scale, and debug Workers applications. No one wants to spend more time than they must turning their ideas into a realized solution. And it is the goal of Workers to make building asynchronous applications in LabVIEW as simple as possible, even for developers that do not have any object-oriented LabVIEW experience. As I mentioned, the development style of the framework is the same as the LabVIEW queued message handler template, because this format is very well known and accepted, and it is easy to understand by the vast majority of developers. So what you see here is a Workers queued message handler. Every Workers queued message handler contains a message handling loop. It is required. This is the loop where messages are processed in the order that they are queued in, depending on their priority. Every worker uses a priority message queue. It's actually the same message queue that's used by the Actor framework, so developers can choose to send messages with either a low, normal, or high priority. If your queued message handler needs to handle LabVIEW events, for example, if it has a front panel, then you can also include an event handling loop if need be. It's possible that a Workers queued message handler also calls or is statically linked to other workers. And if so, these Worker queued message handlers will exist below down here at the bottom of the screen. And throughout the presentation, I'll sometimes be referring to a Workers queued message handler as the Workers main VI, because every Workers queued message handler exists on a VI in the worker called main VI. Okay, so I just showed you what a Workers queued message handler looks like. Fantastic. Thanks for the feedback, guys, because I have no feedback here otherwise. So a Workers application is made up of several queued message handlers, or you can simply say workers. And all of them are linked together to form a tree. If you are familiar with the Actor framework, then the architecture of a Workers application is quite similar, where a root actor would be, here we have a head worker, and the head worker will call other workers that are either statically linked to it or dynamically loaded at runtime. So what you see here is the call chain of all the workers in a workers application. To start a workers application, you would launch the head worker, and then it in turn loads the other workers that are attached to it. And this process will then continue all the way down the tree. In the top right corner of the screen, we have a key for the worker call chain diagram. And you can see that a worker is represented by a solid blue glyph. A worker base class that could represent an abstracted API is represented by only the outline of the blue glyph, and the blocks that have a dashed gray line around them are the workers that are dynamically loaded at runtime. The workers that have no dashed line around them are statically linked to their caller. And by caller, I am referring to a worker that calls or loads one or more workers. So for our example here, the head worker would be the caller of the main UI worker, the motor drive worker, the settings UI worker, and the TCP server worker. Now I'm going to walk through the workers tools that come with Workers 5, and I'll be going through all of the tools in the toolkit, both existing and new, but I'll go into more detail for the new ones. So what you see here is the Workers Tools menu, which is the one place where you can access pretty much all of the Workers tools. The first tool is the Create Add Worker tool, and this tool has not changed in Workers 5. This tool allows you to create new workers and plug them together to build up an application's worker call chain, such as the tree diagram that I showed you on the previous slide. The next tool is the Workers Debug Server, which has been completely redeveloped for Workers 5. The Workers Debug Server is a Windows application that can be loaded either from the Workers Tools menu that you see here, or from a shortcut on your Windows desktop. The Debug Server provides a single location where you can access all of your running Workers applications on a local network. It allows you to jump into your Workers queue message handlers at runtime, and also shows you the sequence of messages that have been sent between workers in an application, and also if and where any errors have occurred. And the Debug Server application can be used to observe and interact with your workers' applications independently of where they are executing. This includes applications running in the LabVIEW development environment, applications compiled into a Windows executable, workers running in a packed project library, or even workers running over a local network on in a real-time target such as a compact Rio. The Workers Debug Server is a very important tool. I personally call it the most important tool in the Workers Toolkit because it adds transparency and access to your workers at runtime, making it very efficient to debug your applications. When you load the Debug Server application, this is the window that will appear. It is the Workers Application Manager. The Application Manager shows you all the workers' applications that are currently running on your local network, including the IP address of the hardware device that the application is running on, and shows you whether the application is running or has shut down. If you have a look at the columns here, it also shows you the worker call chain of the workers that are running in your applications. It shows you the status of your workers, the clone ID of your workers' main VIs, and whether or not a particular worker is statically linked to its caller or has been dynamically loaded at runtime. There is a right-click menu for the Application Manager that you can see here. And besides allowing you to open the front panel or block diagram of a running worker's main VI, in Workers 5, we also have the option to see the message log for a running workers application. So if we were to click on message log here for the selected application, then the selected application's message log window will appear. And this feature is new in Workers 5. The message log shows you the chronological sequence of messages sent and received by the workers in an application, showing you both the NQ and DQ locations of a message. It also shows you where and when any errors have occurred in your workers. And there are options for you to apply filtering at the top here to the columns so that you can, for example, isolate messages sent or received by only a particular worker. Live logging has now been implemented into the new Workers 5 message logs, and this feature allows you to continuously log to file all messages that have been sent between workers in a workers application, as well as any errors that might have occurred. And as I mentioned before, the Workers 5 debug server has been completely refactored and redeveloped for Workers 5, and it is in itself a Workers 5 application. And I plan to release the source code of the debug server application sometime soon under the BSD3 open source license, because I think it's a great example of how Workers 5 can be used to develop multi-process applications in LabVIEW using a mixture of statically linked and dynamically loaded workers. So if you are interested in seeing the source code of the new debug server application, be on the lookout for a post on the Workers LinkedIn or Twitter channel sometime soon. The next tool in the Workers call chain, the next tool is the Workers call chain viewer tool. This tool allows you to view the call chain of a worker's application, similar to the worker call chain diagram that I showed you before in a previous slide at the beginning of the presentation. And this tool is useful for quickly checking the worker call chain architecture of a worker's application. The next tool is the RT Worker Convert tool. Here it is. And this tool was added in Workers 4 when real-time support was added to the framework. This tool is only needed if you are developing workers applications on a real-time target, such as a compact Rio. And its sole purpose is to convert a worker's main VI between its standard re-entrant form to its non-re-entrant form, which then allows you to use a standard LabVIEW debugging tools such as highlight execution and probing wires when debugging your workers' queued message handlers on a real-time target. The next tool is the Worker User Library tool. And this tool allows you to add workers with functionality and an API directly into your projects. So what you see here is the Worker User Library tool. And by default, this tool provides you with a message pump worker, which I have probably used in every single workers application that I've ever created, and also with TCP server and client workers that allow you to communicate and stream data between workers applications over a local network, such as between a workers application running on a Windows host machine and a workers application running on a compact Rio. In Workers 5, there is a new right-click menu that you can see outlined in red here, which allows you to open the new config file editor tool. And this is what it looks like. This tool is new in Workers 5, and it allows you to create and edit config files for workers that you want to add to the Worker User Library, allowing you to build up a library of your workers with functionality and APIs that you can reuse between projects or distribute to a team of developers. The next tool is also new in Workers 5. It's called the Public API Builder tool, and you use it to do exactly that, to build public APIs for your workers. I'm not going to present the tool now because I'll be showing you how to use it later on in the presentation. Under the other tools menu, there is the Create Launcher VI tool, which has been upgraded for Workers 5. This is the new Create Launcher VI tool. And the main addition to this tool is the option to create asynchronous launcher VIs for your workers or worker-based classes. Asynchronous launcher VIs can be used when you want to launch multiple instances of a worker's application, and also when you want to call a Worker's public API from an external source, such as from another LabVIEW framework or from an application that can call LabVIEW VIs, such as TestStand. The next tool is the create the worker base class tool. This tool allows you to create worker base classes, which in turn allows you to create API abstractions for your workers. And I'll discuss how to create and use API abstractions later on in the presentation. The next tool is the change worker inheritance tool. This tool allows you to batch select workers and change the base class that they inherit from. It makes changing the inheritance of your workers very easy. The next tool is the worker message handling loop case viewer tool. This tool is useful if, for example, you receive a worker's application from a colleague and quickly want to get an overview into what message handling loop cases each worker has. It's one place where you can see all the message handling loop cases of all the workers in a project. The next tool in Workers 5 is brand new. It's called the Change Workers Property tool. This is what it looks like. Its purpose is to take the hard work out of changing the name of a worker. Normally, if you want to change the name of a worker, you would need to change the name of the worker class. You need to change, so you'd need to move the worker class and its VIs into a new folder, then delete the old folder on disk, and then rename the worker's input and output control labels on all the static and dynamic dispatch VIs in the worker. So there's no need to do this manually anymore because this tool will do all that for you in one simple click. You can also use the tool to change the alias or icon header text of a worker. These are strings that are used by the scripting tools, and they are stored as tags in a worker's XML file. And now you can change them here with this new tool. In Workers 5, the example projects can now be accessed through the Workers tool menu. And all of the example projects have now been redeveloped from scratch using the new Workers 5 worker APIs. So this is what the new Workers example project tool looks like. Here you can select one of 5 possible example projects. And next to it, you can see the worker call chain diagram for the sample project. In terms of example projects, first we have the workers fundamental sample project. It's the recommended place to start if you are new to the framework. Then we have the continuous measurement and logging sample project, which is the workers version of the well-known LabVIEW project that has the same name. Then we have the DMM HAL Demo project, which is a new example project in Workers 5 that shows you how to create and use a hardware abstraction layer for a DMM. And then we also have 2 more example projects, the Message Pump and TCP Server and Client Worker sample project, and these are part of the Worker User Library tool. And just like with all previous versions of the framework, there is an upgrade tool that allows you to upgrade a Workers 4 project to Workers 5. There is one tool left. This tool is not accessible through the Workers Tools menu. It is instead accessible through a quick drop shortcut from a Workers main VI. For those of you who have used Workers 4, you'll know that the Control 9 quick drop shortcut would create a case label for a worker's visible message handling loop case. But now this quick drop shortcut will open the tool you see here. And you can use this tool to create local API requests for your workers and also to create message handling loop cases that will receive response messages from sub-workers. So I'm done with the tools. Now we can move into the next section, introducing worker APIs. So Workers 5 introduces new worker APIs into the framework, which is a fundamental shift from how messages were sent around a worker's application in previous versions. So let me start talking about what's been deprecated from Workers 4. So firstly, in the top right corner, a worker's public properties are no longer accessible by use of a read accessor VI. I mean, you can do this, but it's been deprecated. A worker's public properties can now be accessed by using a property node on a worker's class wire. The workers for generic messaging API has also been deprecated. This API provided an easy way to send messages back and forth between workers, but the inputs to the API were not typed, making it possible to send the wrong data type to the wrong message handling loop case of the wrong worker. And you wouldn't discover these errors until you ran your code, because the wires would not be broken. Since we now have tools in Workers 5 that can create strictly typed messaging APIs for your workers, the Workers 4 generic messaging API shown here has been deprecated. So when developing the new worker APIs, I decided to avoid creating any type of global messaging system that could send messages between any two workers within a worker's application, and decided instead to make a worker's API accessible locally only to its caller. Each worker has a clearly defined set of inputs and outputs, which are shown here as request messages, which can be sent asynchronously from a caller to a worker, and response messages, which can be sent asynchronously from a worker to its caller. The data types in the request and response messages are owned by the worker itself and not by the caller, meaning that a worker will have no dependencies from its caller and is therefore decoupled from its caller. And because a worker is decoupled from its caller, a worker will have a high reuse value, can easily be shared between projects, and you can also easily add them to your worker user library. Now, because the new worker APIs can only send messages between a worker and its caller, then by default, messages can only be sent up and down a worker's, an application's worker call chain. So for example, if you wanted to send a message from the message pump worker that you see here on the screen to the TCP server worker, then the message pump worker would send a response message to its caller. The main UI worker would send a response message to its caller, and then the head worker would send a request message to the TCP server worker. However, if you want to stream data across a worker's call chain, then you can also do this. But this should be a conscious choice that you make and should be an exception to optimize performance where needed, because it will start to create coupling across your worker's application. There are 4 types of messaging API VIs that you can create in Workers 5, and each VI is strictly typed in terms of both message data and the worker you want to send the message to. Firstly, we have a local request, which is an asynchronous message that a worker can send to itself. Local request VIs and type defs use this blue sideways facing arrow glyph on their icons and take the file name prefix RQL to help you identify the purpose of the VI by both its icon and file name. So to understand how we use the different API VIs, I'm going to use an example project of a simple workers application that you see here. Its worker call chain looks like this. The head worker is worker A, and it has 2 statically linked sub-workers, worker B and worker C. So if we take a look at the main VI of worker A, we can see here that we have worker A's queued message handler. And below it, we have the main VIs, so the queued message handlers of the 2 statically linked sub-workers. So as mentioned, a local API request is an asynchronous message that a worker can send to itself. This means that you can use local request messages. You can use local requests to send messages from a worker's event handling loop to its message handling loop, or between message handling loop cases of the same worker. To create a local API request for worker A, you need to activate the Control9 quick drop shortcut, to open the Create Message Handling Loop case tool. Once the tool is open, you'll need to make sure that this checkbox is checked, called Create Local API Request, VI for this case. Then you can fill out the fields, give your name a request, provide some text for the icon, and provide a description for the request. And then you can press Create New Message Handling Loop Case. After the tool completes, you will see that some new things have been added to your project. Firstly, you will see a new folder has been added to your worker called Local API Requests, and it contains the new Local API Request VI that was just created by the tool. Also, a new message handling loop case has been created in the case structure with the same name as the request, send string, to receive the request message. And the message handling loop case has been added to the case structure under a section header called Local API Cases. The data type of the request, as shown here, has also been added to the new message handling loop case to convert the data sent with the request message to the correct data type. So if we wanted to send a message from this worker's event handling loop to its message handling loop, we would simply drop the local request VI into the worker's event handling loop, wire it up, and when the event fires, a message will be sent to the local request's corresponding message handling loop case, as shown here. Next, we have public API requests. These are asynchronous messages that can be sent to a worker from an external source, such as from a worker's caller, or from LabVIEW code in another framework, or from an application that can call LabVIEW VIs such as TestStand. Public request VIs and type defs use this green downwards facing arrow glyph on their icons, as shown here, and take the file name prefix RQP_ to again help you identify the purpose of the VI. So we would use a public request if we wanted to send a message in our example from worker A to worker B. So to create a public API request, we need to open up the new Public API Builder tool from the Workers Tools menu. So this is the new tool in Workers 5. So first you would select the worker that you want to create the public API request for, and then select the Request tab, and then press Create New Request, which will open up the following window. And similarly to the local request, here you must provide a name for the request, provide some icon text and a description, and then press Create Request. And the tool will create the public request VIs, a message type def for the request, and also a case in the selected worker's message handling loop to receive the public request message. And the new public API request VI will be added to the selected worker. In our example, it's worker B, under the folder Public API Requests that you can see here. So to use this public request VI to send a message from worker A to worker B, we would simply drop this VI into a case of worker A's message handling loop, wire it up, and when this case is called, a message will be sent from worker A to worker B. Now you can see here, what you can see here is that we need to wire to this VI the worker's class wire that we want to send the message to. So not only is the data type of the message strictly typed on the input terminals of the public request VI, but the worker type is too. So for example, if we accidentally wired worker C's class wire to the worker B public request VI, then the wire would be broken as expected. But being able to see this broken wire is one of the advantages of using the Workers 5 API VIs over the generic Workers 4 messaging API. Next up, we have the public API request with reply. This is a synchronous message that you can send to a worker from an external source, much the same as the public API request. However, this VI will wait until it receives a reply message back from the worker, or until a timeout duration has elapsed. public request with reply VIs and type defs use this half green down, half up, purple up facing hieroglyph on their icons and take the file name prefix RWR underscore. To create a public API request with reply, again, you would use the same public API builder tool. And the process is the same as before, but this time you'd select the request with reply tab. I'm not going to demonstrate the process again, but when the tool has completed creating the request, you will see that the new VI has been added to the selected worker in the folder Public API Requests with Reply. And to use this VI to send a public request with reply message from worker A to worker B, you would drop the request VI into a case of worker A's message handling loop, wire it up, and when this case is called, this VI will first send a message to worker B, then it will wait until it receives a reply message back from worker B or until a timeout duration is exceeded. I need to add a word of caution here. Be careful with public API requests with replies. They are an easy way to get data back from a worker, but they are also a blocking call, meaning that the worker that uses the request with reply VI needs to wait before continuing with its data flow. And while waiting, you are preventing the worker's message handling loop from processing any other messages. So only use these where necessary, or when calling a worker's public API from an external LabVIEW application such as TestStand. If, however, you are using a worker's public API from the worker's caller, then it's better to use an asynchronous public response message, which is what I will discuss now. So the last type of public API message is a public API response. This is an asynchronous message that is used to send a message to a caller from a worker. And the caller will receive the response message so long as it is registered to receive it. Public response VIs and type defs have this pink upwards facing hieroglyph on their icons and take the file prefix RSP underscore. Okay, what you see here is the block diagram of worker C's main VI. Here we have a queued message handler with only a message handling loop. Now let's say we wanted to send an asynchronous message from a case of worker C's message handling loop to its caller. To do this, we would create a public API response message in worker C. So again, back to the public API builder tool, select the worker that you want to create the public response for, and then select the responses tab, and then press create new response. And the following window will open up. Here, once again, fill out the details you need for the response, and the tool will create a public response for you. So the public response VI will be added to your selected worker under the following folder: local API responses. The reason it's under the local API folder is because this VI is intended to only be used locally by the worker that owns it to send a message externally to the worker's caller. So to use the public response VI to send a message from worker C to its caller, we would simply drop this VI into a case of worker C's message handling loop, like so, wire it up, and when this case is called, a message will be sent from worker C to its caller. It doesn't know what its caller is, it's just going to send a message to its caller. The caller will have to register the message in order to receive it. So that's an introduction to the local and public APIs that you can now create for your workers in Workers 5. And just like in Workers 4 with case label VIs, you can use the Control-8 quick drop shortcut with all the new API VIs to jump directly to their corresponding message handling loop case to help you trace the flow of your messages around your applications while you are developing. Okay, 10 minutes left, perfect. So the final part of the presentation is about API abstractions. So before going any further, we need to understand what exactly is an API abstraction. So the quickest way to find out anything these days seems to be to ask ChatGPT, which is exactly what I did. So I asked ChatGPT the question, what is an API abstraction? And this is what I got. API abstraction is the process of hiding the complex implementation details of an API while providing a simplified and consistent interface for developers to interact with, facilitating ease of use, modularity, and interoperability in software development. So the most important part of the definition, I believe, is here. Hiding the complex implementation details of an API, which can also be interpreted as separating an API from its implementation code. Okay, that's what API abstraction is. Next, we need to know what HAL stands for. So in the context of software engineering, HAL stands for hardware abstraction layer. So basically, a HAL is a specific usage of an API abstraction. It's an API abstraction used for hardware devices, which fits perfectly into LabVIEW applications, since most of the time we are using LabVIEW software to interact with hardware devices. Here is a representation of a worker's application. If you look closely, you will notice that one of the blocks in the tree is not a worker, it's a worker base class called MotorDrive. And this worker base class is a hardware abstraction layer. In other words, it's an API abstraction for a motor drive. But a worker base class is not a worker, so we need to have one or more workers that inherit from the motor drive base class that can be dynamically loaded in its place at runtime. So for our example, we have 3 workers called motor 1, motor 2, and motor 3 that inherit from the motor drive base class. And each worker provides a different implementation for the API that exists in the base class. So what this allows us to do as developers is to create a fixed API in a worker base class, plug the API into our application, and then separately, later on, whenever, create the implementation for the API in one or more workers. So how do we do this? Well, we create a public API in a worker-based class. So in our example here, we have a set of public API VIs that exist in the base class called MotorDrive. And then we would create the implementation for the API in the message handling loop cases of the workers that inherit from the base class. This will then provide us with a single set of public API VIs in the base class that can be used by the implementations of the API in the 3 workers. Hopefully that makes sense so far. One more thing. To end the presentation, let me show you how to create a hardware abstraction layer in Workers 5. Step 1 is to create a public API in a worker base class. So in the public API builder tool that you see here, as before, select the base class that you want to create the API for. Then go to the Requests tab and create all of the public API requests that you need. I've already done this here, as you can see. So we have all these public request VIs that have been added to the base class in the project. And to create these requests, you follow the same process that I went through before to create public API requests directly in a worker. So that's step 1. Create your request in the base class. Step 2, we want to create the message handling loop cases to receive the public API request messages in a worker that inherits from the worker base, from the MotorDrive base class. So first select a worker that inherits from MotorDrive base class. Here we have selected motor 1, and then select the override message handling loop cases tab in the tool. And then select all of the public API requests that you want to create message handling loop cases for in the selected worker. And then press the button, add selected message handling loop cases to worker. After the tool completes the operation, you'll see that the middle column of the list here will be populated with the word yes in each row, indicating that for the selected worker, a message handling loop case has now been added to receive the public request message from the base class API. So now let's have a look at Motor 1's message handling loop. What you see here is Motor 1's main VI. You can see that the Public API Builder tool has added all of the message handling loop cases to the worker to receive the base class's API request messages. And it is in these cases that we will then add our implementation code for the base class public API. There are two ways to know that this message handling loop case will implement code from a base class API. Firstly, the data type in the message received by this case is a type def that's owned by the base class, and you can see this from the icon header. It says motor and not motor 1. Secondly, the description for this case is written in blue text, meaning that the description for this case is owned by the base class and not by this worker. So what we have done here is created the implementation cases for the base class public API in the Motor 1 worker. So afterwards, we could go ahead and do the same thing for Motor 2 and Motor 3, and that would give us 3 different implementations for the public API VIs in the Motor Drive base class. So let's bring this all together. What you see here is the set of public API request VIs that were created in the Motor Drive base class. And this here is our hardware abstraction layer. This is the API that we have created for our hardware. At the beginning of the block diagram, there is a VI here that says async motor. And this VI is one of the new asynchronous launcher VIs that can now be created in Workers 5. So at runtime, all we have to do is decide which API implementation we want to load, Motor 1, Motor 2, or Motor 3, and use the same set of public API request VIs to send messages to the selected motor. So this demonstrates how you can create a hardware abstraction layer for a worker by abstracting away the API of a hardware device in a base class, inheriting workers from the base class, and then putting the API's implementation into one or more workers that inherit from the base class. We don't need to create duplicated sets of public API VIs for each hardware device. We have one set of public API VIs that can be used by multiple devices, as shown here in the code on the screen. So that brings me to the end of the presentation. I hope you found it interesting. If you would like to try Workers 5 for yourselves, then head over to the VI Package Manager website at vipm.io and do a search for Workers for LabVIEW, and you'll find the landing page. The Workers SDK is the package you want to install into LabVIEW because it will automatically install the 3 packages you need: the Framework Core package, the Development Tools package, and the Debug Server package. And if you want to learn more about Workers, then here is the link to the official Workers user guide site. Here you will find a detailed explanation of all the changes that have been made in Workers 5, and also a walkthrough of the framework and tips on how to get started using Workers, as well as links to the new 60-second tutorial video series that I have started to create for the framework. So I think, wow, 2:45, fantastic. We're right on time. So that's all from me today. I hope you enjoyed the presentation, and thanks for joining. Okay, now there's a lot of questions. I see if I can scroll up. Ooh, okay. I can go through some of the questions. Peter Scarfe, is the timestamp based on the PC or the target? It uses the high frequency timestamp from the LabVIEW palette. So, no, so it's on the target. Yeah, no, it's on the target. So the timestamp is created when you enqueue the message. Yep. So it's from the target. It's not from wherever you're running the debug server application. Can it run on a Linux OS? I don't know. I will need to compile it for Linux OS, but I'm going to be releasing, like I said, the source code for the debug server because it's just a Workers 5 application.
So Peter, I'm going to read out the question so that it saves you from having to scroll up. I mean, so the next question is, can you describe a message pump, which Darren explained as it is a periodic, acquisition or a heartbeat-like messaging? Would you agree with that?
Yeah. So it's just an event. Event handling loop with a timeout, and it's uninterrupted. So we'll continuously pump messages whenever the timeout occurs and send it to the message pump's caller. So it's like a dynamically loadable helper loop, I guess, that you can use in between throughout all your with any worker that needs one.
Yeah. Okay. The next question is the CPD by reference or by value? I don't know what CPD is. It's from Kevin.
CPD, I am not sure.
Class private data.
Class private data. No, it's not by reference. It's data. It's using standard LabVIEW classes.
Yeah. And so can the public request with reply be aborted before timeout? As Carl.
Can the public request be aborted?
So in a synchronous thing.
Correct. I understand.
Yeah.
No, there is no feature for that at the moment.
Okay.
You would have to kill the queue that gets the message back. But no, this feature is not yet implemented.
Enrique asks, how do you define the data type of the messaging API?
You do it yourself. So, it creates a type def for you, and you're free to put whatever you want in it yourself.
All right.
So you just open it up afterwards and then add integers or strings or whatever data types.
Okay. And Glass asks, can you call the parent implementation VI within the overwriting EHL loop? So like, calling the abstract or the parent's implementation.
Can you call the parent implementation VI within the
in a HAL? So
within the event handling loop?
In the message handling loop. So say you have an implementation in the parent, but you want that to be called along with some extension in your child class.
Well, you're always loading the worker. You never, base class is only abstract. It doesn't, you can't instantiate it. So you'll never call the parent. There's only one concrete class, and that's at the end of the inheritance hierarchy. So you're only ever calling the worker.
Okay. And and a lot of people like your UI and all the
thank you
all the effort that you put in, and Darren says he understands how much pain this is to create all the
scripting. Oh yeah. Hours of fun.
And Eli Carey says,
thanks Darren, thanks a lot.
Yeah. And he says, Eli Carey says that he's reviewed your documentation and he's impressed with a lot of the work that you've done. And if I've missed any questions, please.
Thanks, Elijah. Much appreciated. Okay.
I think that's all the questions, I guess. Okay, so Gabriel asks, are there any plans to have not only QMH type workers, but also state machine based ones?
No, we don't have any state machine based workers at the moment. Worker, I guess it could be, you can also create workers from your own worker template. So it would be possible to create a template with a state machine that you could just plug into your applications. That should be possible actually, but it's at the moment we do not have this. It's not part of the framework now.
Okay, Justin says nice presentation.
Thank you.
Reginald asks, do you have interfaces? Do you use interfaces anywhere?
So I had 2 slides about this, but I removed it because I was worried I was going to run out of time.
Okay.
Yeah, that's a good question. At the moment, we don't. The scripting tools don't support interfaces. When you're creating a public request, there is an option in the tool to create a dynamic dispatch public request VI. If you create them as dynamic dispatch VIs, then you can actually create APIs using LabVIEW interfaces. You'd have to do it yourself, though. This is not scripted. I actually do have an example of an application that uses a public API using LabVIEW interfaces instead of a base class. And yeah, I'll probably release this example project so other people can also see how they can do it if they want to do it. So it's possible. Coming.
All right, Eli and Darren, if you are around, I mean, basically, Peter wanted to sort of start a section on NI forums like the DQMH section where you could have a feature request and things like that. So I knew that Jenny Brown used to moderate that. Now that she's not an NI, I did not know who to. Yeah. So okay. Yeah. So yeah, Peter, if you contact Eli, then I think.
Okay. Yep. Thanks. Yeah, we want to get some kind of like online community forum. Yeah. So that would be great,
especially for feature requests, right? I mean, so like
exactly.
The base support for Worker 6. So
yeah, exactly. Exactly.
But I would echo everybody's sentiments that you put in a lot of work, and we're really thankful.
Thank you. Okay. Thanks, Sri. It means a lot.
Thank you.
All right. Thanks, everyone, for taking the time.